Hello everyone, my name is June Stroud and this is my presentation on the mathematics of voting in democracy. The mathematics of voting in democracy is a rarely mentioned subject of mathematics that is utterly fascinating to learn about. Today I will be covering some various kinds of voting and their mathematical formulae alongside the implications said formulae have on voting and democracy. So what is voting? What we think of as voting is really two separate parts: how we gather information and how we find a winner. To gather information, we will be using preference ballots. And to show the information we gather from preference ballots, we will be using preference schedules. This is a preference schedule. If you look at the top row, you can see that it has the number of votes of candidates in specific orders. So, if we look at this last column here, we can see that 6 voters chose C as their first option, B as their second option, and A as their third option. So, to find a winner is the next step. There are many ways to find a winner, but no way is without flaw. The first way we will go over is the plurality method. The plurality method is when the option with the most first place votes wins. So, in this example, A has 10 first place votes, B has 1 first place vote, and C has 9 first place votes. This means that A wins using the plurality method. Next is the border count method. The border count method is when each place is assigned points. When assigning points, the last place is worth 1 point, and then you add a point going up each place. So, if you have n places, then first place will be worth n points. Whoever has the largest amount of points in the ends wins. So, using the same example preference schedule from earlier, we can see that A has 43 points, B has 32 points, and C has 45 points. This means that C wins. Note how to find the point value for each square, you multiply the point value by the number of votes for each square, and then you add them up. So, since C won, there is a clear difference when using the border count method and when using the plurality method, which the differences between the voting methods should be remembered because it is important for later. Next is the plurality with elimination method, also known as the sequential runoff method. So, in the sequential runoff method, you take the option with the least number of first place votes. In this example, that's B, and you eliminate it. You just completely remove it from all of the options. So, when you do that, you're left with these. You repeat this process until you are left with only one left. So, since A has 10 votes and C also has 10 votes, this would really end up with a tie. So, when using the plurality with elimination method, also known as the sequential runoff method, you end up with a tie. Next is the method of pairwise comparison. When you're using the method of pairwise comparison, you have many one-on-one matchups, like a fun little sports game except for it's voting. When each time an option wins, they get a point, and if it ends in a tie, they both get half a point. So, we're going to go to our example. So, the first one-on-one is A versus B. So, A has 13 votes, and B has 7 votes. Notice how, if the first option is not one of the ones you're comparing, you go to the next option that is. Since A has more first place votes, has more votes than B, A wins this round, meaning A has 1 point. Next is A versus C. In A versus C, A has 10 votes and C has 10 votes. So they both get half a point. So A is up to 1.5 and B is up to half a point. And B still has 0. Then we have B versus C. In B versus C, B has 5 points and C has 15 points. So B is still not getting a point, and C has gotten a point, meaning C is at 1.5 points and B is at 0 points. A is also at 1.5 points. So there is a tie between C and A when using the method of pairwise comparison, using our nice little example schedule. When finding the exact number of one-on-one matchups for using the method of pairwise comparison, you're going to need to use this lovely formula we have here of n parentheses n minus 1 divided by 2. What that really means is, since n is the total number of candidates, you're going to take n times n minus 1 dividing by 2. So if you have 6 candidates, you're going to have 15 one-on-one matchups. That's a lot of math. Then, finally, we have weighted voting. Weighted voting uses quotas. You're going to try to pass a quota. Quota is represented by a tiny little q. Voters are called players because people think it sounds cool. Players are represented by big P's, and each player has a little subtext that tells which player it is. Since n is the total number of players, it goes from P1 to P2 to P3 and so on and so forth until Pn. Weight is the total amount of power each player has. So W1 is the weight of player 1, W2 is the weight of player 2, and so on. It is important to note, before I move on, that quotas need to be over half of the total weight, but less than the total weight. Next, it's important to know what a dictator is. A dictator is a player who can pass the quota all by themselves. In this example, we can see player 1 is a dictator. If they say yes, then it shall be. Passes the quota all by itself. A player who can stop something from passing has veto power. In this example, we can see all players have veto power because all players are required to vote yes to pass the quota. Lastly, a player who has no power is a dummy. It's important to note here that if the total amount of weight is equal to the quota, then it still passes. So, here we can see poor player 4 is a dummy because no matter who it joins, it will not make any difference. It could join any group or leave any group and nothing would change. So, when trying to figure this out, there are 2 indices that are helpful for finding the power of each player. First, we can use the Bantzef Power Index. The Bantzef Power Index looks at groups called collisions. To find the total number of collisions, you're going to be using this lovely little formula here, where 2 to the power of n minus 1. Collisions are kind of interesting groups because you start by grouping each player by themselves, then grouping them by groups of 2, groups of 3, so on and so forth until everybody's in one big group. To find the power of each player, you're going to need to know what a critical player is. A critical player is a player that when they leave a collision, they're going to make it lose. It's going to lose if they're not there. So, to find the power of each player, we're going to need to know this wonderful formula here. Pi is the player, or I guess the player number. Bi is the total amount of times that that player has gone critical, and T is the total number of times everybody has been critical. We can put this into practice using a lovely little example. We love examples. So, we have all of the different words. We have all the different collisions listed out in order. You can see that we start by figuring out if they win or lose. We see that all of the players individually lose, and once they've gotten into groups of 2, they win. The critical players for each group are listed below, and we can notice that each player is critical 2 times. If you look over here, you can see that no player is critical when all 3 of them are there, even though it's a winning combination. The thing is that when you are listing out multiple of them, if it's already won, no matter who you remove, since it already wins, even if you don't add another one on there, means that none of them are critical, because if you remove one, it's not going to change anything. So, knowing all of this information, we can plug it into our lovely formula over here. We know that the total number of times any player has gone critical is 6. And we know that every player has gone critical twice. So, using this, we have figured out that each player has a power of 2 of 6, or 1 of 3, or 33%. This would mean that they all have veto power because they all have equal percentages. That's why this is really helpful. So, they all have veto power. Next is the Shapley-Shubik Power Index. Big mouthful to say, but very fun. Would recommend. The Shapley-Shubik Power Index uses pivotal players instead of critical players. The difference between pivotal players and critical players is that pivotal players are when you add a player to a group, it becomes a winning group instead of a losing group. It's important to note that it uses sequential coalitions instead of normal ones. And when you're using sequential coalitions, you need to use angle brackets instead of curly brackets. If you show up and show somebody your worksheet and you have curly brackets when it's a sequential coalition, they're gonna mark it down on that. Don't want that. So, when you're using sequential coalitions, it's really just a grouping of everybody. But it tells you which order they joined in. So, in this sequential coalition, player 1 has joined first, player 2 has joined second, and player 3 has joined last. Nice and handy and dandy. To find the total amount of sequential coalitions, when using the Shapley-Shubik Power Index, you have to take this wonderful thing here, which is n, as you should know by now. N is the total amount of players, and you're going to take it, and it's going to be a factorial, so you're going to need n factorial. To find the player, the value of each player, or the power of each player, you're going to take this lovely formula here, which is pi, which is the player, equals si, which is the amount of times it's been a pivotal player, divided by n factorial, which is the total amount of different sequential coalitions. We have a lovely example here. Using the same weights from earlier, we can see it's all listed out here. Notice how each sequential coalition has only one pivotal player. This is because after you add a pivotal player, it's a winning combination, and you cannot make a winning combination win again. That's not how things work. So, we know that n is 3 because there are 3 different candidates here. Because that's the total number. And so we know that the factorial of 3 is 6. So we know that we're going to be dividing it by 6. We look over here and see that we look over here and we see that each player has been a pivotal player 2 times. So player 1, for example, has been a pivotal player 2 times. So putting it into this formula, 2 divided by 6, which is really similar to 2 divided by 6, which, as you know earlier, equals 1 divided by 3, which equals 33%. If you look here, you notice the other players also are pivotal players 2 times. Shocking. Which means that they're all worth 33%, which means they all have veto power. Using the Shapley-Shubik power index and also using the Banseff power index causes you to have very similar results. In this case, you have the exact same results, but oftentimes you have slightly different results. But they are always very similar. So, is it fair? This is where it all comes together. As you look betwixt the options, do you see which one is the fairest easily? No, they all look pretty similar to none try die. But there's this handy dandy theorem called Arrow's theorem, made by Arrow. He says in his theorem, also known as Arrow's impossibility theorem, that no voting system can pass all of his little conditions, which we will go over. But it's important to note that depending on what source you use, his conditions will be slightly different, because no one can seem to agree on these things. So, first off, we're going to go over the majority criterion. The majority criterion is when an option gets over 50% of the first place votes, it should win. Makes sense, right? You'd think so. But, using this example, and specifically using the border count method, C would win, even though A has over 50% of the first place votes. What's up with that? Because that breaks the majority criterion. Next is the quorum correct criterion. That is when a candidate wins every round in a pairwise competition. They should win. So if they have a bunch of one-on-ones and it wins every time, it should win. Would make sense. So using this example and using plurality, A would be lovely enough to win, even though C would win every one-on-one competition. This breaks the quorum correct theorem criterion. The quorum correct criterion and makes us seem a little silly. Next is the Montanicity criterion. Montanicity criterion. It's when a candidate wins an election, and then when there's a re-election, there is no change, or a change in favor of them, they should win. Would make sense if everything seems to be going better for them. They should win, right? I've already won once. But using this example and using the plurality of elimination method, you can see that, well, beautiful. So A wins using the plurality of elimination method, for this first election. But suddenly they had a re-election. I don't know why. It's because it's helpful for us. So suddenly some people were like, oh wow, wait, A wins. I should vote for them. Because reasons. So they start voting for A. But suddenly, using the same voting method and using this exact chart, this exact schedule, we can see that this time C wins. But all of the change has only been in favor of A. Well, that means that then the plurality with elimination method in this specific example broke the Montanicity criterion. We also have the independence of a relevant alternatives criterion. Big mouthful to say, but basically, if you remove an option, or if there's a third option, or if votes for a third option change their places, the two options that you're looking at should stay ordered the same. This one seems to be everybody's favorite, yet they cannot agree, so this is the definition we're going to be using. Lastly, we have the no dictator rule. Basically, don't have a dictator. Understandable. So, what does this tell us? What does this mean for democracy? All of the mentioned types of voting break these, showing flaws in every kind of voting system mentioned. And possibly every voting system out there, which shakes just our idea of democracy overall. Because it is mathematically impossible to have a perfect democracy. That is even without mentioning insincere voting. Insincere voting is often common with the plurality method, which is in fact the kind that we use in the United States, where a candidate that's less likely to win isn't voted for, even if it's the preferred candidate, because in fear that a worse candidate is going to win if you vote for the less liked candidate. Which isn't really a good democracy if you can't vote for who you truly want. So, it tells us that there is no perfectly fair democracy, and that there never will be. And that's okay. In summary, the mathematics of voting and how it affects democracy leads to shocking answers. I'm sure you didn't come here today to be told, hey, the voting of mathematics kind of rocks our fundamental thoughts on democracy. But that's okay. Because the fairest democracies aren't fully fair, and they never will be. And that is just the conclusion we have to come to. These are the works cited. An important side note here, these are especially for specific scenarios. It's not going to break a rule constantly, always, just in very specific scenarios. So you don't get all depressed thinking, my God, everything is going to be sad when it's math democracy. Thank you for watching.